In module 7 of chapter 10, that is some applications of differential geometry, we shall learn geometry of space time in general theory of relativity. Actually, in this module we shall learn a very important space time called Friedmann-Robertson-Walker space time. Friedmann is named after Alexander Friedmann, a Russian scientist. Robertson is Howard P. Robertson, an American scientist, and Walker is an England based scientist. They framed this space time for expanding universe. So, in this module at first we shall learn the Friedmann-Walker space time, and nextly we shall learn that the geometry of the space time for constant curvatures, that when the Gaussian curvatures are +1 or 0 or -1, then we shall learn the geometry of the space. And lastly, we shall learn in this module the Friedmann equation, which is the very basis of Big Bang theory in cosmological world. So, let us start the Friedmann-Robertson-Walker space time. So, the title of module 7 is applications of differential geometry in general theory of relativity and cosmology, continued, because in module 5 and 6 we have seen some applications of differential geometry in general theory of relativity and cosmology. Here the learning objects are the geometry of space time. Actually, here we shall learn the Friedmann-Robertson-Walker space time. Secondly, geometry of the three spaces of constant curvature. So, let us start the first one, that is the geometry of space time. Now, if the space coordinates x1, x2, x3 are constant along the geodesics, such coordinate system is called co-moving system. In this coordinate system, the line element of the space time takes the form in this way: ds square equal to dt square minus hab dxa dxb, where ab is running from 1 to 3. hab actually is a function of t and x. Now, if the line element of space is given by this one, d sigma square equal to qab dxa dab by in this form e to the power lambda dr square plus r square d theta square plus sin square theta d phi square, that is independent of time here. So, where lambda is only the function of r, then the metric for non-vanishing components of the Ricci tensor can be obtained by this: r11 equals to lambda 1 by r, r22 equals to cosec square theta, r33, and they are equal to 1 plus r by 2 e to the power minus lambda, lambda 1 e to the power minus lambda. Now, this we have obtained in our earlier modules also, the calculations we have done in our earlier modules. So, we have just represented it in this form, and by this equation we have the following differential equations: this lambda 1 by r equal to 2k to the power lambda, and 1 plus r by 2 e to the power minus lambda to the lambda to the power 1 equals minus e to the power minus lambda equal to 2k r square. Now, if you solve this one, we have this expression e to the power minus lambda equals to 1 minus k r square, and thus we get d sigma square equal to dr square by 1 minus k r square plus r square d theta square plus sin square theta d phi square, where theta and phi are the angular coordinates of the space time. And thus, the 4-dimensional line element will be like this: ds square equal to dt square minus a square t, and this expression. Now, we just define the new radial coordinate in this form, that means we give a transformation like this. Then the equation reduces to the conformally flat form. We have known earlier that what is conformally flat space. So, the line element for that form will be this one, ds square equal to dt square minus a square t by 1 plus 1 by 4 k r bar square whole square, and the last portion in the third bracket. Now, writing k equals to mod k kappa for k not equal to 0, we get where k kappa is equal to plus minus 1, and the rescale the radial coordinate as r star equal to in this form mod k to the power half r, then the line element takes in this form. Now, defining r t equals to s t by mod k to the power half for k not equal to 0 and equal to s t for k equal to 0, the above line equation will becomes, after the dropping the star symbol, is this one, ds square equal to dt square minus r square t in the third bracket, dr square by 1 minus kappa r square plus r square within the first bracket d theta square plus sin square theta d phi square, and the third bracket is closed, where this the value of kappa is equals to 0 plus minus 1. Now, this is known as Friedman-Robertson-Walker line element. The above line element is known as Friedman-Robertson-Walker line element after the name of Friedman, Robertson and Walker. They gave this form within the 1920 to 30 when they are working on expanding universe. Actually, this line element is the exact solution of the Einstein's field equation for general theory of relativity. And according to the cosmological principle and Weyl postulate, what we have learned in our previous module, the space time of the universe is described by the Friedman-Robertson-Walker line element, because from cosmological principle we have seen that the space is homogeneous, and so for cosmological principle and Weyl postulate we have that the space time of the universe is described by the FRW line element. Further, the geometry of the hypersurface at t equal to t0 is given by this form, d sigma square. So, d sigma square is the metric for the hypersurface, where the time is taken as a constant. So, this is the only space coordinates are the variable. So, here d sigma square equals to r naught square within the third bracket dr square by 1 minus kappa r square plus r square d theta square plus sin square theta d phi square. Where this r naught is termed as the radius of the universe at the instant t equal to t0. So, in the first section of module 7 of chapter 10, we have learnt about Friedman-Robertson-Walker spacetime. This line element is the exact solution of the Einstein's field equation for general theory of relativity. And in this line element, we have obtained a term kappa which have different values plus minus 1 or 0. So, now in the next section we shall learn about the nature of the space when the values of kappa will be plus 1 or 0 or minus 1. So, let us see the geometry of the space for constant curvature. So, in this section we shall learn the geometry of the three spaces of constant curvature, and we shall learn the nature of the geometry when the value of kappa is 0 and plus minus 1. So, first let us consider that kappa is equal to plus 1, and this one is named as closed model. From the three space line element of the previous equation, we see that there is a singularity as r tends to 1, and it is a coordinate singularity. So, for k equals to plus 1, this singularity appear. Now, we introduce a new coordinate chi as r equals to sin chi to remove this singularity, and the line element becomes d sigma square equals to r naught square within the third bracket d chi square plus sin square chi within the first bracket d theta square plus sin square theta d phi square. Now, let us introduce a set of 4 variables x1, x2, x3, x4 defined as x1 equals to r naught cos chi, r2 equals to r naught sin chi sin theta cos phi, x3 equal to r naught sin chi sin theta sin phi, and x4 equals to r naught sin chi cos theta. So, substituting these values, we get this one x1 square plus x2 square plus x3 square plus x4 square equals to r naught square. So, a 3 space in 4 dimensional Euclidean space, and also the line element, the equation becomes d sigma square equal to dx1 square plus dx2 square plus dx3 square plus dx4 square. Thus, the 3 space is embedded in a 4 dimensional Euclidean space, and also the 3 space can be regarded as 3 sphere in 4 dimensional Euclidean space. Now, the range of the 3 angular coordinates chi, theta, phi over the 3 space are 0 less than equal to chi less than equal to pi, 0 less than equal to theta less than equal to pi, and 0 less than equal to phi less than 2 pi. And also the line element, the 68 becomes d sigma square equals to this, just we have obtained earlier this one. So, this is the figure for the previous line element, and the space structure is like this. the theta, chi are the angles, and this is a sphere. The figure shows the 3 space with one dimension suppressed, that is x 3 equal to 0, that is phi equal to 0. And also from the figure we have that the two surfaces chi equals to constant appear as circles, that is two spheres of surface area. This one, the double integration 0 to pi and the phi is 0 to 2 pi r naught sin chi d theta, r naught sin chi sin theta d phi, and after the integration we are getting 4 pi r naught square sin square chi. So, the two sphere has vanishing area at the two poles and has maximum area 4 phi r naught square at the equator. Also, the 3 volume bounded by the 3 space has the expression this one, chi equals to 0 to pi r naught d chi, theta equals to 0 to pi r naught sin chi d theta, and phi equals to 0 to 2 pi r naught sin chi sin theta d phi. So, finding this integration we get the volume as 2 pi square r naught cube. And justification for r naught as the universe of the, it is the radius of the universe. Therefore, the topology of the 3 space is closed and bounded, that is compact, while that of the whole space time is cylindrical, as it is like this r cross S 3 with cosmic time represented by r. So, the whole space time is cylindrical. Now, for kappa equals to 0, we have a flat and open type of space, and in this case the spherical polar type transformation will be like this: x 1 equals to r sin theta cos phi, x 2 equals to r sin theta sin phi, and x 3 equal to r cos theta, with r equals to r naught small r, and this transform the 3D line element, and the equation 67 becomes like this. So, d sigma square will be equal to d r square plus r square within the first bracket d theta square plus sin square theta d phi square, and by this transformations we get it is dx 1 square plus dx 2 square plus dx 3 square. And this shows that the 3 space is a 3 dimensional Euclidean space. So, the topology of the space time is the 4 dimensional Euclidean space, that is R 4, and is open and flat in nature. Next, we see that when the kappa is equal to -1, and in that case it is coming to an open space, and again by transformation of radial coordinate as r equals to sin hyperbolic chi, the 3D line element 67 simplifies to this one, d sigma square equal to r naught square within the third bracket d chi square plus sines hyperbolic square chi, and within the first bracket d theta square plus sin square theta d phi square. And which shows that the 3 space cannot be embedded in a 4 dimensional Euclidean space. However, Similar to the case when kappa equals to plus 1, if we consider the transformation of the coordinate variables as in this form, P equal to r naught cos hyperbolic chi, q equal to r naught sin hyperbolic chi sin theta cos phi, u equal to r naught sin hyperbolic chi sin theta sin phi, and v equal to r naught sin hyperbolic chi cos theta, we have this form d sigma square equals to minus dp square plus dq square plus du square plus dv square. And also the coordinates are restricted in this form, p square minus q square minus u square minus v square equal to r naught square. So, substituting these values of p, q, u, v, we get this form. Thus, the 3 surface is embedded in a flat Minkowski space of signature plus 2. From the line element we can consider, we can see that it is a flat Minkowski space, and in fact, the 3 space is a 3D hyperboloid in 4-dimensional Minkowski space as shown in the figure, this one. So, it is a hyperboloid in 4-dimensional Minkowski space. So, the structure of the space will be like this. Now, as before, chi equals to constant, 2 surfaces are 2 spheres of surface area, a chi equals to 4 pi r naught square sin hyperbolic square chi. So, the surface area of 2 spheres increase from 0 to infinity as chi ranges from 0 to infinity. And here the topology of the space time is R4 and is open in nature. So, in our last discussions we have seen that different type of topology is coming out due to the values of the kappa, and we have mentioned only the simplest possible topology for the above 3 cases, and however, it is possible to have other complicated topologies also. Now, we shall derive the Friedman equation for general theory of relativity. Now, the following 3 ingredients of relativistic cosmology, we have the geometry of the space time as Friedman-Robertson-Walker model. Here d square equal to dt square minus r square t within the third bracket, this one, this expression we have seen it earlier. Now, the cosmic space time should be perfect fluid with energy momentum tensor T mu nu equals to rho plus p u mu u nu minus p g mu nu. And we have discussed in our earlier modules that what is perfect fluid space time, where u mu is a unit time like vector and rho is the energy density and p is the thermodynamic pressure. So, with this T mu nu, the Einstein's field equation for general theory of relativity is this one, G mu nu equals to kappa T mu nu. These things we have learned. and choosing the co-moving coordinate system with u a equals to 1 0 0 0, that is the components are like this, then the explicit form of the evolution equations will become 3 r dot square by r square plus 3 kappa by r square equals to kappa rho. And 2 r double dot by r plus 3 r dot square by r square plus kappa r square equal to minus kappa p. With the energy conservation relation, this one rho dot plus 3 r dot by rho within the bracket rho plus p equals to 0, where dots denotes the derivatives. Now, these equations are known as Friedmann equations, and they are the fundamental equations in relativistic cosmology. Actually, these Friedmann equations are the basis for the Big Bang theory in modern cosmological model. So, in module 7 of chapter 10, we have learned two very important concepts for general theory of relativity. The first one is Friedmann-Robertson-Walker spacetime, which is very important spacetime, and it is the exact solution of the Einstein's field equation in general theory of relativity. And from there, for different values of the curvature, we have seen the geometry of the spacetime, that is the geometry of the three spaces for constant curvatures. And also we have obtained the Friedmann equations, which is very important concept for cosmological model. Now, with this we end this module, and also we shall end our chapter, that is chapter 10, and some applications of differential geometry. There are many other applications in various fields, but we have not included these things. So, with these things we end also our chapter 10.